The first thing that I want to do here is just introduce you to some known trig identities. These ones are called the reciprocal identities, and we actually already talked about them, I think. Yeah, we did. But they're on your formula sheet. Cosecant of theta, so cosecant of any angle is equal to 1 over the sine of that angle. Secant theta is 1 over the cosine theta, and cotangent theta is 1 over tangent theta. You should be fairly familiar with these ones by now. These are called identities because they're statements that have been proven to be always true. So for any angle, cosecant is 1 over sine. For any angle, secant is 1 over cosine, and so on. The next ones that are also on your formula sheet are these quotient identities. And we talked about the first one already. Tangent theta is sine theta over cosine theta. Cotangent theta equals cosine theta over sine theta. You're going to get to be using these a lot when you're doing the trig identities. These ones are very common to use, especially the tangent is sine over cosine. There are 3 different things that you may be asked to do. Well, 2 different things really. Verify an identity and prove an identity. And we're going to look at 2 ways to verify and then 1 way to prove. So the difference between those verify and prove, do you know what that is? You don't do a lot of work with proofs in high school math. If you take math in university, you might do a fair bit more. But to verify something means to show that it does work, but it's not the same as proving. Proving means that it's absolutely always true. Verifying means it seems like it's always true, but it's not quite the same thing. So 2 different ways to verify something like this. Secant x equals tangent x over sine x. This is not a trig identity that's on your sheet, but this is one that we think is true. We think that secant x is tan x over sine x. First, we're going to verify. So the 2 ways to do that are by graphing and by filling in a value. So I'm going to do the filling in a value part first. I can choose anything that I want to for x. I'm going to choose pi over 4. So what I would do is secant pi over 4 equals tan pi over 4 over sine pi over 4. So this is the verifying part. So what I'm going to do is try to show that it's true when the angle is pi over 4. And if it's true when the angle is pi over 4, then it's probably true for all the other angles as well. So pi over 4, I need that special triangle, 1, 1, root 2. And then actually calculate the secant of pi over 4. So here, secant is 1 over cosine. So root 2 over 1. Right? Cosine would be adjacent over hypotenuse, so secant is hypotenuse over adjacent. Root 2 over 1, or just root 2. The tangent of pi over 4, opposite over adjacent, is just 1. And the sine of pi over 4 is opposite over adjacent, so 1 over root 2. The left side of that I can't simplify any further, it's just root 2. But 1 over root 2 simplifies to what? Root 2. So I end up with root 2 equals root 2, which means that I verified it because both sides are equal. So that tells you it works for pi over 4, which makes me think it's probably true for all values of x. So making a graph of each side, so y equals secant x and y equals tan x over sine x, when you look at the graph, they look the same, which is another way of verifying that it's an identity. But then you're asked to prove that it's an identity. And this is the part that I like, that's kind of fun. I'm just going to rewrite it over here.
You can't see anything.
Oh, right, you can't see this. Better? Oh, you can see it. Okay, so I rewrote that so that I can prove it. And there are steps that we have to follow to do a mathematical proof. And actually, mathematical proof is very specific in the way that it works. What we're going to do here is one type of proof, but there are lots of different things and lots of different rules when it comes to proofs. So for this type of proof, the way that it's going to work is you need to choose one side or the other of the equation to work with, and you're only allowed to work with that side. So you're not allowed to rearrange this. You're not allowed to simplify one side and then simplify the other. You have to choose one side and stick with just working with that side. And your goal is to take one side of the equation, change it around so that it looks like the other side. The way you're going to decide which side to choose is you choose the one that looks more complex, because it's easier to go from something complex and simplify it than it is to take something simple and expand it. So which side here would you say is more complex? The right. So I'm actually just going to draw a line down the center, and I'm going to work only on the right side of that line. This one's pretty easy because it's the first one we're doing. What we need to do is use there's a number of things. We could look for any algebraic simplifications we can do right away. Things like if you have two fractions, getting a common denominator and adding them together, or sometimes factoring, those kind of things. But here, there's nothing like that. We need to think about those identities that I just told you about, which you'd already known about most of them, but how can we take those and replace something that's in here? So if we look at tangent, there's something that we can replace tangent with. Sine over cosine. So I'm just going to do that. I'm going to go equals sine x over cosine x over sine x. That sine x is going to be stay the same. Changing tangents, cotangents, secants, and cosecants into sines and cosines is a common first step when you're proving identities, especially when they're fairly simple ones like this. Even in some of the more complex ones. Now I'm going to do just an algebraic simplification. Sine x over cosine x divided by sine x, which comes out to 1 over cosine x. I'll just write out how we get there. So it's sine x over cosine x multiplied by 1 over sine x, right? It's dividing by sine x, so multiplied by the reciprocal. And then the sine x's can cancel out. And this turns into 1 over cosine x. And we have an identity that tells us that 1 over cosine x is equal to something else. What's it equal to? Secant x. And now, left side equals right side. Over here, this part of it, we verified that this is sometimes true. Here, we proved that it's true. And it's actually not true for every value of x, which Alex pointed out earlier, but it's proving that that is a trig identity. The points that it's not true for are the non-permissible values, which is the values that make the denominator here in the first one equal to 0, or the points where part of the function is undefined. All right, I'm going to give you 3 more identities here. These are also on your sheet. They're called the Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. This one is so great when you get to use it, because you have this big thing in your expression, sine squared theta plus cosine squared theta, and you're just able to take it out there and put in a 1, which is so nice. 1 plus tangent squared theta equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. The other thing with these Pythagorean identities is that you can change them around. Well, actually, the other ones you could as well rearrange them. So we could say something like, if we came up with something like a cosine squared theta, but we wanted to change it into a sine, that's equal to 1 minus sine squared theta. Right, because I just subtract sine squared theta from both sides to get the cosine squared theta by itself. So these identities, you can rearrange and use them differently. We could say that sine squared theta is equal to 1 minus cosine squared theta. Or for the next one, we could say that tangent squared theta is equal to secant squared theta minus 1. Like any way that you can rearrange them. I'm not going to write out all the arrangements, but any way that you could rearrange them, it's okay to do that. This is just kind of their most common form. Here's another thing that we want to prove. Sine squared x minus sine x is equal to negative sine x cosine squared x. Okay, I'm going to skip that one because when I tried to verify it, it didn't seem to be true. So let's try this one instead. This one, when we graphed it verified, it's definitely works for the graph. So we need some ideas about how to simplify this. Which side are we going to work with? The left. Obviously, it's going to be difficult to take a 1 and change it into that big expression. So we'll work on the left, and we want to change that into a 1. Any ideas? You could take that tangent and change it into a sine over cosine. What's that? Or you could factor out a cosine squared x. That's what I was thinking about doing. I can see that there's a common factor here, and it might be helpful to factor it out.
Wait, would tangent squared x actually be sine squared x over cosine?
Sine squared x over cosine squared x, yeah. So that'll work, I think, too. Either of these are going to work. Let's try this one. I might try it both ways just for fun. You could factor out a cosine squared x. Or I'm just going to do, well, I'll just do this one, then I'll do the other. If I do this, is that 1 plus tangent squared x an identity?
Yeah.
What is it? It's equal to secant squared x.
I already got it.
I'm just going to show you.
Actually, a little bit quicker.
Here's the last one that we're going to do. Sine x over cosine x plus cos x over 1 plus sine x equals secant x. Again, with this one, we're going to work with the left side and try to take all of that stuff on the left and change it into secant x. And really, I am going to, in the back of my head, think I probably want to change it into 1 over cosine x, because then that I can easily change into secant x. But I'm not going to work at all with the right side. I'm going to work with the left. And what I notice right away is that I have 2 terms on the left and only 1 on the right. So I want to make that into 1 term. How do you add fractions? Common denominator. So I'm going to erase that line because I think I'm going to need a lot of space here. Common denominator will be just those 2 multiplied together, cosine x multiplied by 1 plus sine x. And I'm not even going to bother to expand it in the denominator because I think I'm actually going to probably want it in factored form. Because I can already see where the answer is going to come from. Right now I have a cosine x on the bottom. I want a cosine x on the bottom so that it'll equal secant x in the end. So what I have to do here is sine x multiplied by 1 plus sine x plus cos x multiplied by cos x. So I took the denominator of the first one and multiplied by that on the second one, and then the denominator of the second and multiplied the first one by that. This is just algebra, basic algebra. I'm going to expand and simplify that numerator. So I'll multiply it out. Sine x times 1 plus sine x is sine x plus sine squared x. And then the cosine x times cosine x is cosine squared x. And I still have that denominator. Cos x times 1 plus sine x. Do you guys see this yet, how it's going to work out? Where's the identity that we're going to use now? Sine squared x plus cosine squared x right here. What's that equal to? 1. So I end up with sine x plus 1 over cos x times 1 plus sine x. Then what? Cancel out the 1 plus sine x. And you'll remember, hopefully, from grade 11, that when you want to cancel things like this, it has to be a whole factor that you're canceling. It can't be individual terms. So I can't cancel an individual, like if I had sine x plus 1 and I had a sine x on the bottom, I couldn't cancel just the sine x. It has to be the whole factor. So this whole factor cancels with this whole factor. And on top, I'm left with a 1, and on the bottom, a cos x, and 1 over cos x is equal to secant x, which is what we wanted right there. So again, left side equals right side.